That happened. Good. What's the domain of that one? Negative infinity, positive infinity. So remember, when we multiply two functions where their domain exists in both graphs, that's where the graph exists, the whole thing, correct? Well, both of these are negative infinity, positive infinity. So what is the domain of this function? Negative infinity, positive infinity. So when we go to do our intervals for concavity and intervals of increase, decrease, we're going to have a full number line with arrows. Yeah? Yeah. Okay. I want you to get the critical numbers of the first derivative. How do we do that? Find the first derivative. Set equal to what? 0, because we're finding horizontal tangent slopes. Because the horizontal tangent slopes are where the max, mins, and points of inflection occur. Correct? Go. So, let's do the first derivative. So, f prime of x equals g. What's the derivative of f? 1 plus, guys, try please, f times the derivative of g. And then I told you, we had to remember, and I said to you, the key thing for this last unit is if you can take out GCFs and get them all broken down, this unit's really, really easy. And if you can't do that with derivatives, this unit is impossible. There is no in between. So when we look at these two terms, whenever you do a derivative of a numerical base to a variable exponent, you use chain rule. You rewrite it, law on the base, variable to the exponent. Just happens that e to the x is still e to the x because the other two turn to 1s, correct? So I can take an e to the x out. When I take an e to the x out, I'm left with 1 plus x minus 8. If this doesn't just go away, when I take an e to the x, I'm left with 1. And so I'm left with e to the x, x minus 7. And I have to set it equal to 0 because I'm trying to find the horizontal tangents. What happens at horizontal tangents is a little reminder, guys. Yeah, you get equal to 0. And what actual things on the graph? Max, mins, and points of inflection. Also, your critical numbers could give you asymptotes now. Yes? You could end up with an asymptote if you have a denominator that has a variable in it. But yesterday, all we dealt with was polynomials, correct? So their domain was negative infinity, positive infinity, so everything worked. This particular example's domain is negative infinity, positive infinity, so I'm not going to get any asymptotes either, or points of discontinuity, which are called removable discontinuities in calculus. Okay? So we have to set these equal. E to the x equals 0. This is where I lose people because their log information falls out of the brain. X minus 7 equals 0. So I get x equals 7 as a critical number. How the heck do I get a variable exponent to come down? We log. Convert it to a log. That's exactly what we do. So remember, every single time we've solved anything else, we have always just had our variable down at the bottom. We either divide, we multiply, we square root, we cube root, we seventh root, we third root, whatever. But we learned that when the variable's in the exponent, the only way we can solve that is converting it to a log. That's why we did logs and exponentials in 30. So the base of my exponent becomes the base of my log. So I get log base e of 0 equals x. What is log, or this would be ln of 0 technically. What is ln of 0? It doesn't exist. There's no solution. Remember, whatever's beside a log or a ln, we talked about this, it has to be positive. Correct? You can't have a 0, you can't have negative numbers. That's how we got extraneous roots, extraneous solutions when we were solving 30-1. We had to state our values. And if we had a variable or anything beside a log, it had to be greater than whatever the heck that value was. It can't equal 0. Remember your basic log graph has an asymptote here, and then it would go like this, right? So that's the greater than that. All right, so no solutions. Some people will say extraneous. You still are struggling then. Extraneous means I got a solution, I plugged it back in, I can't get an answer, right? So go log 0 in your calculator. Actually, go ln 0. It's just below log. What does it do? It's that. What? That's not him. That's Mrs. Listener. Okay. So, our critical numbers, I guess our critical number is x equals 7. So that's cool. Sometimes they just ask for critical numbers of the first derivative. You'd be done. Sometimes it asks for intervals of increase, decrease, or maxes and mins. So we'd have to keep going, correct? And we go to our number line, and the reason why we found the domain is we now know that the number line is from negative infinity to positive infinity every single time because my domain is from there to there. If my domain was like greater than 7, I would start at 7 with a closed dot and put an arrow to infinity, right? So your number line represents your domain. So in here I have the number 7. Then I need to pick a number lower than it. Like I always do, I'll pick 0 and then 8. So I have to plug that into f prime of x. Why am I plugging into f prime? Because I want to see what the derivative is doing below that value. Wherever the derivative is positive, the graph is doing what? Increasing, and it has to make sense to you because the tangent slopes are positive, correct? If the tangent slopes are positive, it's increasing. If the tangent slopes are negative, it is decreasing. So we need to test f prime of 0, and I always plug it into the e to the x, x minus 7. So I'm going to get e to the 0, x, or 0 minus 7. E to the 0 is what? Anything to the power of 0 is 1. So this is 1, and then negative 7. So is my answer going to be positive or negative? Negative. It actually is negative 7. Do I need to find that, though? No. The only time I actually have to find out what that actual y value is if I'm drawing the first derivative. Now I know I have a coordinate on the first derivative at 0 and negative 7. Right? That's an actual coordinate. If I'm not drawing the first derivative graph, I just need to go positive, negative, negative. Right? Run a test point. Then I'm going to do 8. F prime of 8 equals e to the 8 minus 7. Now some people are like, this is in the non-calculator section. I can't do e to the 8. Well, e to the 8 is positive. That's all we care about. And 8 minus 7 is positive. What's positive times positive? Positive. That's it. Right? Like we don't need the actual value. So there's no reason to panic. Also, on the AP exam, they'll sometimes just give you the first derivative. They don't even make you find it. They'll say the first derivative is this. Determine the intervals of increase, decrease. They give it to you. Sometimes they give you the first derivative and then ask for concavity. So they give you the first derivative and you have to derive that to get the concavity. Right? So it just depends on what they give you. So interval of decrease is what? Negative infinity to 7. Interval of increase. Seven to infinity. And what's happening at 7? I always draw it. So it's decreasing to increasing. What's happening at 7? It's not decreasing. It's a good thing to remember that. Minimum of 7 and a what? How do I get the what? Plug it into the original. So I don't remember my original. It's f of 7. It was e to the 7 minus 8. So it's negative e to the 7. That's what they will write. Can you type the original into your calculator into your y equals? The original. So when I typed it in, this computer doesn't let me bring up my calculator anymore. I have to go talk to someone. It says it's expired, but it isn't. You're getting a graph like this. I made it to negative 1200. Because remember, your minimum is at e to the 7, which is giant. Okay? So I made it. So what's it doing? It's decreasing to 7, and then it's increasing from 7 to infinity. Right? There's a minimum down there. It makes sense. Yes? we showed that by first derivative. Now we're going to talk about concavity. So we need to get the critical numbers of the second derivative. Now, I'm going to tell you right now, if it's a polynomial, everyone paying attention to me? If it's a polynomial, when you find the first derivative, before you factor it or anything like that, that's the easiest thing used to get to your second derivative, because you can just use power rules, correct? When you're doing anything but a polynomial, your actual GCF form is usually your easiest, because you have an f and a g and you just product. Okay? So it is in the most simplified form best to use. So f prime of x equals e to the x minus 7. So then we have to, if we're asked anything about concavity or points of inflection, we need to go to the second derivative, f double prime of x. Now, some people think they have to find all that other information. If I just ask you for concavity, do you need anything to do with increase, decrease, max, mins, or anything like that? No, you find the first derivative, you use that, find the second derivative, and then answer questions. So it's not like it's asked every single time. So we're going to get g times f prime plus f times g prime. Taking e to the x out, and we're left with x minus 7 plus 1. So we get e to the x minus 6. 0. You will learn to appreciate e to the x's. Because e to the x's by themselves always result in no solution, because it's going to be e to the x equals 0 again. Right? E to the x equals 0, which is log base e of 0 equals x, which is no solution. Then x minus 6 equals 0, x equals 6. So the critical number of the second derivative is x equals 6. I don't know what I'm writing. X equals 6. And when we go to do our number line, it's still from negative infinity to positive infinity, because that doesn't change. The domain of the original is the domain of everything we're going to do from now to infinity in this question. So now I have to run test points on the second derivative, correct? I'm going to use 0 and 7. You could use 5 and 7. I like personally just using 0 if I get the choice, I think. And 1s. I really like 1s as well. So we're going to go f double prime of 0 equals, and I always put it into the simplified form. So e to the 0, and then 0 minus 6. E to the 0 is positive because it's just 1. 0 minus 6 is negative. What's the positive times the negative? A negative. And what is that in the second derivative? Decreasing, which is what you guys kept telling me yesterday, and I wanted to crawl under my desk. Yes. Concave down. No crawling under my desk today. Over the night, things have solidified in your head. I wanted to yesterday because I was sad, because I kept giving you second derivative negative, and you'd be like, decreasing every time. I'd be like, ah. Okay. F double prime of 7. E to the 7, 7 minus 6, positive times positive. So what's this one? Concave up. So we know that this graph is concave down from negative infinity to 6, concave up from 6 to infinity. And what's happening at 6? Point of inflection. The critical numbers of second derivative give points of inflection. The only time it's not a point of inflection is if at the very beginning we decided it was a point of discontinuity or removal discontinuity calculus or an asymptote, correct? If it's none of those things, if the domain is XER, that's point of inflection. Critical number of second derivative. So it's at 6 and something. Where do we plug it in to get the something? The original, because we want that, the point of inflection on the original graph, correct? So we want f of 6, which equals e to the 6, 6 minus 8, I believe. The original was 8. So we get e to the 6 times negative 2, which you could leave it like that, but that looks stupid. So I'm going to rewrite it as negative 2 e to the 6. Yeah? Okay. Trying this one out now. New example. Okay. Type that one into your y equals. I know we won't always have an option to type it in for now. So this graph, what's the domain of it? It's in front of your face. What's the domain of this graph? It goes like this. Negative infinity, positive infinity. The reason why is because when the 3 is in the bottom, what is that? Cube root. We've talked about this since grade 10. Remember, every single thing that you do in calculus starts in grade 10. Even before that a bit, but for the most part, 10 is 10 common, 20 is pre-calculus, 30 is pre-calculus, and we're in calculus. It all builds up to calculus. So these are cube roots. Is there any values I'm not allowed to take the cube root of? I can take negative cube roots, I can take positive cube roots, correct? Because this is a cube root and every single one of them are cube roots, there is no restriction on the domain. But if those were 2's on the bottom, or 4's, or 8's, or 10's, then we have to actually check and see what x values are underneath that square root, fourth root, or whatever, because they have to be positive. Okay? So when it's a cube root, or a fifth root, or a seventh, when there's a 3, 5, 7, 9, whatever on the bottom of that, that's the best thing ever because your domain isn't restricted. Because you can take cube roots, fifth roots, seventh roots of any value. Okay? This question itself isn't a hard one to find a derivative of, because we can just use what? Power rule. So f prime of x equals 2/3 times a half x, subtract 1 off of 2/3, what am I left with? Negative 1/3. Minus 1/3 x, drop 1/3 by 1, negative 2/3. 2's cancel off, so I'm left with f prime of x equals 1/3 x to the negative 1/3 minus 1/3 x to the negative 2/3. Now we talked about this. I told you that we will always take out the smallest exponent. Now in chain rule, that always turns to a 1. That doesn't mean in this it does. We didn't do any chain rule, right? We just did power rule. So we have to check and make sure what happens. So I'm going to take the 1/3 out. What's smaller, 1/3 or 2/3? In negative form. 2/3. Because the smaller one's the one that's further down on the number line, correct? To the left. And negative 2/3 is smaller down. It's further down, sorry. So we get x to the negative 2/3 taken out. Okay, what's left over? Take a third out, take a third out. That's gone. Then I'm going to take x to the negative 1/3, and I'm going to divide it by x to the negative 2/3, because when I take out GCFs, that's what I do. I divide, correct? When I divide the same base, what do I do with the exponents? Subtract. So I'm going to get x to the negative 1/3 minus a minus, so plus 2/3. So I'm going to get x to the third. Now some people are like, but Mrs. Lepp, you said it always became 1. Yeah, when we did a chain rule. We didn't do a chain rule. This is just power rule, right? So we're going to get x to the 1/3 here. And then when I take x to the, so 1/3 x to the negative 2/3 out of negative 1/3 x to the 2/3, I'm left with a minus 1. All right? And we have to find out where this equals 0. This looks a lot harder than it actually is. These are not hard to do. So we have two critical spots that we're going to take and set equal to 0. Two factors, technically, right? We have 1/3 x to the negative 2/3 set equal to 0. And then we have x to the 1/3 minus 1 equals 0. Okay, let's discuss this. I'm going to get rid of a third by multiplying by 3. X to the negative 2/3 equals 0. Cool. How do I get rid of negative 2/3? Don't say I take the negative 2/3 root. I want to get this to be a 1. So what am I going to multiply this by? Negative 3/2. What is 0 to any exponent? 0. So our one critical number is 0. So whenever you have a monomial sitting in front to whatever power it is, it doesn't really matter, you will get a critical number of 0. That monomial coefficient. Okay. Then we're going to add 1. I get x to the 1/3 equals 1. How do I get rid of a third? Raised to the power of 3/1, correct? What's 1 to any exponent? 1. So my critical numbers of the first derivative are x equals 0, 1. True? Yes? Then I go to do my number line for intervals increase, decrease. I know that it's negative infinity to positive infinity because we've discussed that these are all cube roots, and cube roots can't be restricted because you can put anything under a cube root, negatives and positives. Our critical numbers are 0 and 1. And then we have to plug in below 0. I'm going to do different color. So I'm going to do negative 1. Here I'll go 0.5. And then maybe 2. And I have to plug them into the first derivative to find, because wherever the first derivative is greater than 0, it's increasing, because you have tangent slopes that are positive. Wherever the first derivative is less than 0, it's decreasing, because you have tangent slopes that are negative. Wherever the first derivative is equal to 0, you have maximums or points of inflection. Possibly asymptotes. Can't have any here, because the domain, once again, is XCR. So I'm going to plug it always into my simplified version. So I'm going to get f prime of negative 1. So I'm going to get 1/3 negative 1 to the negative 2/3. And then negative 1 to the 3rd minus 1. Now, because we don't do a ton of these, can you guys follow along with me? Grab a calculator. We're going to do a little bit of discovery. So in your calculator, I want you to put negative 1 in brackets. We're going to do a little bit of testing with negative values to whatever exponents we put it to. So, say I put negative 1, paying attention, negative 1 to the 3. What's going to happen? Negative 1 has to be in brackets, so it's negative. And then go negative 1 to the 8. It's going to be positive. Most people are good with those. Even exponents result in a positive, and odd exponents result in a negative. Most people are good with that. But what happens when it's a fraction? So let's do this. Negative 1 to the half. Gets mad at us, because what's a half just the same as? Square root. You can't take square root of a negative, right? So it gets mad. Says there's no solution. Okay, go negative 1 to the 3rd. We get negative 1, because the cube root of negative 1 is negative 1. Okay, do this. Negative 1 in brackets to the 2/3. Negative 1 to the 2/3. What do we get? 1, because what are you doing first? Squaring the negative 1, then cube rooting it. Do you understand what we're saying when it's 2/3? Because that 2 is underneath the radical. So you square that number first, then cube root it. Yes? Make sense? Okay, now do this. Go negative 1 in brackets to the negative 2/3. You're going to get 1. Let's do something that's not a 1. Ready? So in brackets, can you guys do this, please? Negative 2 in brackets to the negative 2/3. Negative 2 to the negative 2/3. Yeah, you're subtracting. What do you get? Okay, if I do this, negative 2 to the 2/3, what am I technically doing? Negative 2 squared, and then keep rooting it, correct? What happens when I get a negative, though? Grade 10. How do you make a negative positive? There's no equal signs or anything. How do I make that negative positive? Move it to the denominator. So negative 2/3 is actually this. 1 over. To make it positive. So this, for negative 2/3, my next step, all right here, negative 2 to the negative 2/3. What you would do is you would go 1 over negative 2 to the positive 2/3. Remember how to make it positive is you move it to the denominator? Does that make sense? So when you have negative exponents, it's actually a fraction. Understanding a little bit? Remember your calculator's gone for half your test. So, not usually the most advanced crazy questions though, to be honest. Okay, so let's go back to here. 1/3 is positive. It's a 1/3. So this one we're going to go, paying attention, negative 1 to the 2. Ignore the negative part first. What's negative 1 to the 2? 1. What's the cube root of 1? And when I drop it to the bottom, it's 1. So it's still positive. Correct? What's negative 1 to the 1/3? What's the cube root of negative 1? Negative 1 minus 1? So it's negative. So what's a positive times a positive times a negative? Right? Then we do 0.5. F prime of 0.5. 1/3, 0.5 to the negative 2/3, 0.5 to the 3rd, minus 1. All right, so 1/3 is positive. 0.5, let's figure out what the sign is. So we're going to get 0.5 squared. It's still positive, correct? The cube root of a positive is positive. And then 1 over a positive is still positive. So this is a positive. Right? And then this one, 0.5 to the 3rd, is less than negative 1. So we're going to get a negative. So this will be a negative again. And then we have 2. So f prime of 2 equals 1/3, 2 to the negative 2/3, and then 2 to the 3rd minus 1. So I'm going to get positive. 2 to the squared is positive. Cube root of that's positive, and then it'll be 1 over positive, so it's positive. And then 2 to the 3rd is 1.25 minus 1 is positive. So it's positive. So we decrease, decrease, increase, correct? Now this thing here, what happens when it decreases to decreases? What do we get here? This is a point of inflection. This one decreases to increases, so this is a what? Minimum. We agree? If I want to get the second derivative, remember this. We're all paying attention. If to get the first derivative I use power rule, which is the easy one, polynomials I use power rule. This one I use power rule. I'm not going to go down here and use this to get my second derivative. I'm not going to use this to get my second derivative. I'm going to use this power rule up here to use power rule again. So if my first derivative to find the second is power rule, use your top one to get your second derivative, power rule again, right? Don't use this. You know what I'm saying? You can. That's way more awful than just doing power rule. Does that make sense? Okay. We're going to go over one last one. One where it's not XER. Really important when your calculators are taken away. Because if I type that into my calculator, I might be able to get its domain, correct? But if my calculators are taken away, I don't know what the domain is. I do, however, know how to get the domain of this one, and I do know how to get the domain of this one. Correct? Remember, division is a little different. Addition, subtraction, and multiplication, where the two exist is where your domain is, yes? Division, where the two exist is where your domain is, yes? But you also have to look for non-permissible values of your denominator to add on to it. So, this first one is a radical. What is its domain? Greater than or equal to what? 0. So it's 0 to infinity. If you want to look at it in a different way, I sometimes like looking at it as a number line. So that one is 0 to positive infinity. Okay, cool. I'm going to do the other one is black. What's the domain of this one? It is from, it's a line, so it's negative infinity to positive infinity, but x can't equal negative 1. Because we have an asymptote. Now, how do I know that's an asymptote and not a removable discontinuity? It's not on the top. So you would have to cancel off the top and the bottom in order to be a removable discontinuity. The factor is not on the top, so I know it's a vertical asymptote. Okay, so this is 0 to infinity, but I also know that negative 1 can't exist. What's cool about this graph? It already doesn't exist because that top one kicked it out. So you would have lucked out if you had forgot to do NPVs, right? So when I go to do anything about this graph, intervals of increase, decrease, if I go to do concavity, any of that stuff, I'm now only going to have a number line from 0 to infinity, right? This part doesn't exist because it can't exist because my graph isn't XER. Yeah? So please go type this one into your y equals so you can look at it. First derivative. In order to do the first derivative, guys, what are we going to have to do? Quotient rule. I know you're waiting for this day. Don't worry. It's here. So we get G F prime. So I'm going to go G prime equals 1. F prime equals 1/2 x to the negative 1/2. So we're going to be doing that chain rule kind of thing. So we're going to get G F prime minus F G prime. And then what you can't forget is G squared. Okay. So what can we do? What can we do? GCF out what? We're just looking at the numerator. We have to take out the x to the negative 1/2, and we have to take out the what? Half in front. We've talked about this, right? So we have to take out the 1/2, and we have to take out the x to the negative 1/2. Let's see what's left over. Half x to the negative 1/2 is gone, so I'm left with 1 plus x, which is substantially nicer. Now if I take a 1/2 out of 1, what does it turn to? Guys, a 2. 1 divided by 1/2 is 2. What happens when I take an x to the negative a half out of an x to the half? I get x to the 1. Didn't really need brackets, but if it was a binomial, I would have to remember to distribute that minus sign through, correct? It's a monomial, so we're good. All over 1 plus x to the 2. Now remember, the 2 can drop to the denominator. The x to the negative a half can drop to the denominator. So in the top, we're left with 1 plus x minus 2x. So that's 1 minus x in the top. All over. 2 drops to the denominator. X to the half drops to the denominator. It becomes x negative half becomes x to the half. And then we get 1 plus x squared. So we have to take all of those things, even the denominator ones. They all result in critical numbers. So let's go over here. We have critical numbers. We have 1 minus x equals 0. So 1 equals x. That's one of the critical numbers. We agree? Then we have 2x to the half equals 0. Divide by 2. X to the half equals 0. Raised to the power of 2. X equals 0. And then we have 1 plus x equals 0. X equals negative 1. Why is x equals negative 1 critical? It's where the asymptote existed if I didn't have this, right? So it's a critical number, but is it a max or a min or anything? No. It's also outside my domain, so it's actually not a critical number. Why is 0 a critical number? It's an endpoint, it's where my domain starts. So really, 1 is the only one that can be a max or a min, or a point of inflection, correct? This one can't be, it's a restriction. This one can't be, it's where it starts. This is where. Okay? So let's look at our number line now. We have a number line. It goes from 0 to infinity. The people who stink at these questions are the ones who completely forget to figure the domain of the equation out at the very beginning. Because they'll go from negative infinity to positive infinity. They'll still have the negative 1 on here. The 0 they think is critical. There's a max or a min. But it's where the graph actually starts. So the only true max or min that can come from this is the 1. So I can go 0.5. And I can go 2. And I can type it into my derivative. So I'm going to do this one over here. I'm going to go f prime of 0.5 just because it's going to take a bit more space. And I'm going to plug it into that. So I'm going to get 1 minus 0.5. Guys, stop. 2 and then 0.5 to the half. 0.5 plus x squared. 1 plus 0.5. Now, I want to prove a point here. I don't want an answer. I just want if it's positive or negative. You guys will try and get an answer and then it gets convoluted and hard. It's not. We just go, okay, on the top I have 1 minus 0.5. Well, that's a positive on the top. We agree? Then here I have 2. Well, that's positive. Times 0.5. What's the square root of a positive? A positive. Do I care what the actual answer is? No. And what's anything squared? Positive. Anything squared is positive. So I have on the denominator a positive times a positive times a positive. So in my denominator I have a positive. In the numerator I have a positive. So what's my result? Positive. So I know that here it is increasing. Do you see what I'm saying by if I just want to know if it's increasing or decreasing a positive sign? I'm not figuring out any math there. I'm just using positive and negative signs. F prime of 2. So I'm going to get 1 minus 2 over 2 times 2 to the half, and then 1 plus 2 squared. Right? And I just get signs. What's 1 minus 2? Negative. Over 2 is positive. 2 to the half, anything square root positive is positive. Anything squared is positive. So I end up with a negative over a positive. What does that result in? Negative. A negative divided by a positive is a negative. We agree? So then we're decreasing here. And our graph showed that. Yes? Then we know we are increasing to decreasing. So what is 1? A maximum. You have a maximum at x equals 1. How we get the actual maximum, though, is we plug it into f of 1, which was square root of 1 over 1 plus 1, which is a half. So we have a maximum at 1.5. So do you see how important it is to get that domain at first? Do you see how important it is to know function operations unit from 30-1? That everyone thinks is small and not important. It's extremely important. Especially the domain and range part of it. Especially the domain part of it. Okay? Adding, subtracting, multiplying, dividing. So important so that you know how to get the domain of these. And composition was so important because that is how you do chain rule. This was composition when you have another function inside another function. Okay? Here are your questions. This is your homework from the text.